Right now, inside every atom in your body, there is something violent happening. Inside every single proton, there is a storm. Not a gentle hum of particles sitting quietly in place, but a raging, churning chaos of energy so intense that it generates almost all of the mass you feel when you step on a scale. And the thing responsible for this chaos is something most people have never heard of. It's called a gluon. It sounds harmless. It sounds like glue. But a gluon is not just sticking things together. It is doing something far stranger. It is creating mass out of pure energy. It is holding reality together by constantly tearing itself apart. And what it actually does inside a proton is one of the most stunning things in all of physics. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something you were probably taught in school. At some point, maybe in a chemistry class or a physics lesson, someone showed you a picture of an atom. And in that picture, the atom looked neat. It looked organized. There was a nucleus at the center, drawn as a tight little ball of protons and neutrons. And around the outside, there were electrons orbiting like tiny planets going around a sun. It was a clean, tidy diagram. And somewhere along the way, someone probably told you that protons and neutrons are made of smaller things called quarks. 3 quarks per proton, 3 quarks per neutron. You might have seen a diagram of that too. 3 little coloured spheres sitting inside a circle, arranged in a triangle, maybe connected by lines. It looked simple. It looked calm. It looked like the quarks were just sitting there, like marbles in a bowl, doing nothing in particular except being quarks. That picture is wrong. Not slightly wrong. Not a harmless simplification. It is fundamentally, deeply, almost dangerously misleading about what is actually happening inside a proton. Because inside a real proton, nothing is sitting still. Nothing is calm. Nothing is arranged neatly in a triangle. What is actually happening inside a proton is closer to a violent storm than it is to a quiet arrangement of particles. The interior of a proton is one of the most energetic, turbulent, chaotic environments anywhere in the known universe. And the thing responsible for that chaos, the thing that drives the storm and holds it together at the same time, is a particle called a gluon. Now, you might have heard the word gluon before. It sounds like glue. And in a very loose, very simplified sense, gluons do act as a kind of glue. They are the particles that hold quarks together inside protons and neutrons. But calling a gluon glue is like calling a hurricane a breeze. It technically points in the right direction, but it misses everything important about what is actually going on. Gluons do not simply stick quarks together the way tape holds paper to a wall. What gluons actually do is far more interesting, far more violent, and far more essential to the existence of matter than most people ever realize. And to understand what a gluon actually does inside a proton, we need to start from the beginning. So let's talk about forces. In your everyday life, you experience forces all the time. Gravity pulls you toward the earth. When you push against a table, the table pushes back. When you rub your feet on a carpet and touch a doorknob, you feel a little spark of static electricity. These are forces you can feel directly, forces that operate on a human scale. In physics, we know of 4 fundamental forces that govern everything in the universe. Gravity, which holds planets in orbit and keeps your feet on the ground. Electromagnetism, which governs light, electricity, magnetism, and the chemistry that makes your body work. the weak force, which is involved in certain types of radioactive decay, and the strong force, which holds atomic nuclei together. Of these four, gravity is the weakest. That might surprise you because gravity feels powerful. It holds the Earth in orbit around the Sun. It keeps galaxies together. But on the scale of individual particles, gravity is almost unimaginably weak compared to the other forces. If you took two protons and compared the gravitational attraction between them to the electromagnetic repulsion between them, the electromagnetic force would be about 10 to the 36th power times stronger. That is a 1 followed by 36 zeros. Gravity is that weak at the particle level. But the strong force is something else entirely. The strong force is the most powerful force in the known universe. It is roughly 100 times stronger than electromagnetism at the distances inside a proton. It is about 10 to the 38th power times stronger than gravity at those scales. The strong force is what holds quarks together inside protons, and gluons are the particles that carry this force. Every fundamental force in nature is carried by what physicists call force-carrying particles, or bosons. Electromagnetism is carried by photons. The weak force is carried by particles called W and Z bosons. Gravity, if it has a carrier particle at all, would be carried by a hypothetical particle called the graviton, which has never been detected. And the strong force is carried by gluons. When two quarks inside a proton interact through the strong force, they do so by exchanging gluons. One quark emits a gluon, and another quark absorbs it. This exchange is what creates the attractive force between them. It is what holds the quarks together. It is what makes the proton a bound object instead of just three quarks flying apart in different directions. But here is where things start to get strange. To understand gluons, you need to understand something called color charge. And no, this has nothing to do with actual color. The word color is just a label physicists use because they needed a way to describe a property of quarks and gluons that has no everyday analogy. In electromagnetism, the property that determines how particles respond to the electromagnetic force is electric charge. Electrons have negative charge, protons have positive charge. Opposite charges attract, like charges repel. Simple enough. In the strong force, the equivalent property is called color charge, but color charge is more complicated than electric charge. Electric charge comes in two types, positive and negative. Color charge comes in three types, which physicists call red, green, and blue. Every quark carries one of these three color charges at any given moment. And just as electric charges must balance out in ordinary matter, color charges must also balance out. A proton must be color neutral. This means the three quarks inside it must carry one red, one green, and one blue color charge, which combine to form a colorless or white state. Think of it like mixing colored light. If you combine red light, green light, and blue light in equal amounts, you get white light. Similarly, combining a red quark, a green quark, and a blue quark gives you a color-neutral proton. Now, here is the key thing about gluons and color charge. Gluons themselves carry color charge. This is radically different from photons. Photons carry the electromagnetic force, but photons do not have electric charge. A photon is electrically neutral. It does not feel the electromagnetic force itself, it just carries it between charged particles. But gluons are different. Gluons carry color charge, which means gluons feel the strong force. Gluons interact with other gluons. This is one of the most important facts in all of particle physics, and we will return to it in much greater depth later. But for now, Just hold that in your mind. Photons do not interact with each other. Two beams of light can pass through each other without either one being affected. But gluons do interact with each other. They pull on each other. They can emit other gluons. This single fact changes everything about how the strong force works and what the inside of a proton looks like. So let's go inside the proton and see what is actually happening. Forget the textbook diagram with three neat little quarks sitting in a triangle. What is really happening is this. There are three quarks, yes. They are called valence quarks because they are the quarks that define the proton's identity. Two up quarks and one down quark. These three quarks are not sitting still. They are moving at speeds close to the speed of light, bouncing around inside a region that is roughly 1 femtometer across. A femtometer is 1 quadrillionth of a meter. That is 0.0000000000000000001 meters. It is a distance so small that it is roughly 100,000 times smaller than an atom. The proton is tiny. And inside that tiny space, quarks are screaming around at nearly the speed of light. But the quarks are not the whole story. Not even close. The quarks are constantly exchanging gluons. Constantly. Every moment, quarks are emitting gluons and absorbing gluons. These gluons fly between the quarks, carrying the strong force, keeping them bound together. And because gluons carry color charge, they are not just carrying the force passively. They are participating in it. They are part of the system. They are players in the storm, not just messengers passing notes between quarks. Let me try to give you a sense of how active this environment really is. Imagine you are watching a room where three people are standing in a triangle, throwing balls back and forth to each other. That is the simple picture. Three quarks exchanging gluons. Now make it more realistic. The people are not standing still. They are sprinting at nearly the speed of light, zigzagging wildly across the room. The balls they are throwing, the gluons, are also flying at the speed of light. And the balls themselves can split into more balls mid-flight. And those new balls can interact with each other and with the people. And sometimes a ball will spontaneously turn into two new people who appear out of nothing, exist for a brief instant, and then vanish again. And all of this is happening in a room so small, you would need 100,000 of them side by side to span a single atom. That is what the inside of a proton looks like. It is not static. It is not calm. It is a seething, boiling, raging storm of quarks, gluons, and energy, all crammed into one of the smallest spaces in nature. And the gluons are at the heart of this storm. They are what drive it. They are what sustain it. Without gluons, the quarks would fly apart and the proton would not exist. Without gluons, there would be no protons, no neutrons, no atomic nuclei, no atoms, no molecules, no stars, no planets, no life, nothing. Gluons are what hold the most basic building blocks of matter together. Now, let me be more precise about what a gluon actually is in physical terms. A gluon is a fundamental particle. It is one of the elementary particles described by the Standard Model of Particle Physics, which is our best theory of how particles and forces work. A gluon is a boson, which means it is a force-carrying particle. Specifically, it carries the strong force between quarks. A gluon has no mass. It is massless, just like a photon. It travels at the speed of light, just like a photon. It has a property called spin, with a value of 1, just like a photon. In many ways, a gluon looks like the strong forces version of a photon. But there is one critical difference that changes everything, and we've already touched on it. A gluon carries color charge. A photon does not carry electric charge, so photons do not interact with each other through electromagnetism. But a gluon carries color charge, which means gluons interact with each other through the strong force. This is so important that it is worth repeating. Gluons feel the force they carry. Photons do not feel the force they carry. This one difference between gluons and photons leads to completely different behavior for the strong force compared to electromagnetism. Here is one way to think about it. Imagine you have two electrically charged particles sitting near each other. They interact by exchanging photons. The photons fly back and forth between them, carrying the electromagnetic force, but the photons themselves do not interact with each other. If you pull the two charged particles farther apart, the force between them gets weaker because the photons spread out and the connection between the particles weakens. This is why electromagnetism gets weaker with distance. It follows what we call an inverse square law. Double the distance, and the force drops to 1/4 of what it was. Now imagine two quarks inside a proton interacting through gluons. The quarks exchange gluons, and those gluons carry color charge. Because the gluons carry color charge, they interact with each other. When a gluon is traveling between two quarks, it does not just sail through empty space like a photon would. It interacts with other gluons along the way. This interaction between gluons means that the strong force does not spread out and weaken with distance the way electromagnetism does. Instead, something very different happens. But we will explore that behavior in much greater detail shortly. For now, what matters is this. The interior of the proton is filled with gluons. Not a few gluons passing quietly between quarks, but a dense, churning sea of gluons constantly being emitted, absorbed, splitting, merging, and interacting with each other. At any given instant, if you could somehow freeze the proton in time and count everything inside it, you would find not just 3 quarks. You would find 3 valence quarks, plus a large number of gluons, plus additional quarks and antiquarks that have popped into existence temporarily from the energy of the gluon field. This is sometimes called the quark-gluon sea or the parton sea, where parton is a general term for any particle found inside a proton. How do we know all this? How do we know the proton is not just 3 quiet quarks? The answer comes from experiments. Starting in the late 1960s, physicists at the Stanford Linear Accelerator Center began firing high-energy electrons at protons. The idea was simple. If you shoot something small and fast at a proton and measure what happens to it after it bounces off, you can learn about the internal structure of the proton. It is the same principle as throwing a ball at an object in the dark. By studying how the ball bounces, you can figure out what the object looks like even if you cannot see it directly. These experiments were called deep inelastic scattering experiments, and their results were revolutionary. When electrons were fired at protons at high enough energies, the electrons did not bounce off the proton as if it were a smooth, solid ball. Instead, they bounced off as if they were hitting small, hard, point-like objects inside the proton. The proton had internal structure. There were things inside it. These experiments, led by physicists Jerome Friedman, Henry Kendall, and Richard Taylor, provided some of the first direct evidence for quarks inside the proton. The 3 physicists won the Nobel Prize in Physics in 1990 for this work, but the experiments revealed something else, something unexpected. When physicists analysed the data carefully, they found that the quarks inside the proton only accounted for about half of the proton's total momentum. The three valence quarks were carrying only about 50% of the momentum that the proton should have based on its known properties. Something else was carrying the other half. That something else was gluons. The gluons inside the proton, constantly flying between quarks and interacting with each other, carry a significant fraction of the proton's total momentum. In fact, later and more precise experiments showed that gluons carry roughly half of the proton's momentum. This was direct experimental evidence that the proton is not just made of quarks. It is made of quarks and gluons. The gluons are not just theoretical constructs or convenient mathematical tools. They are real physical entities inside the proton, carrying real momentum and real energy. They are as much a part of the proton structure as the quarks themselves. In some ways, they are more important. Think about what this means for a moment. When you look at the proton, you might think it is defined by its quarks. 2 up quarks and 1 down quark. Those quarks give the proton its identity. They determine its electric charge. They determine what kind of particle it is. But the quarks are not doing most of the heavy lifting inside the proton. The gluons are. The gluons carry about half the momentum. The gluons generate most of the energy. The gluons create the binding force that holds everything together. The quarks are like the named characters in a story, but the gluons are the ones actually making the story happen. This is why calling gluons glue is so misleading. Glue is passive. You put glue between two surfaces, and it just sits there, holding them together without doing anything interesting. Gluons are nothing like that. Gluons are dynamic, active, energetic, and essential. They are constantly being created and destroyed. They are constantly interacting with quarks and with each other. They are generating enormous amounts of energy in the tiny space of the proton. They are the reason the proton is a storm and not a box. Let me take a moment to emphasize just how many gluons we are talking about. If you could take a snapshot of the proton at any given instant, you would find 3 valence quarks, but you would also find, depending on the energy at which you probe the proton, dozens or even hundreds of gluons. The number fluctuates constantly because gluons are always being created and absorbed. But the point is that at any moment, the proton contains far more gluons than quarks. Gluons outnumber quarks inside the proton. They dominate the interior. The proton is, in a very real sense, more gluon than quark. If you had to describe the proton by what it mostly contains, you would not say it is made of the quarks. You would say it is made of gluons, with a few quarks mixed in. And there is something even stranger going on. Because gluons carry so much energy, and because energy and mass are related through Einstein's famous equation, the gluons contribute enormously to the proton's mass. We will explore this in great detail later. But for now, just hold on to this fact. The 3 quarks that define the proton, the 2 up quarks and 1 down quark, have a combined mass of only about 9.1 mega-electron-volts divided by the speed of light squared. The proton's actual mass is about 938.3 mega-electron-volts divided by the speed of light squared. The quarks account for only about 1% of the proton's mass. The other 99% comes from the energy of the gluon field, and the kinetic energy of everything moving around inside the proton. This is perhaps the most astonishing fact about the proton. almost all of its mass does not come from the mass of the particles inside it. It comes from the energy of the gluon-driven storm. Everything you see around you, every rock, every tree, every building, every person, is made of atoms. And the mass of those atoms comes overwhelmingly from their protons and neutrons. And the mass of those protons and neutrons comes overwhelmingly from the energy of gluons. You are not heavy because the fundamental particles inside you are heavy. You are heavy because of the energy of gluons, the energy of the strong interaction, the energy of the storm inside every proton in every atom of your body. This brings us to a crucial point about what the proton really is. The proton is not a container. It is not a bag holding 3 quarks. It is a dynamic system. It is a bound state of the strong interaction, a structure that exists because of the continuous, violent, energetic exchange of gluons between quarks. The proton exists not because quarks decided to sit together, but because the strong force carried by gluons creates a bound system that is stable. The proton is the storm, and gluons are what make the storm. There are exactly 8 types of gluons. Why 8? This comes from the mathematics of the strong force, which is described by a theory called quantum chromodynamics, or QCD. The strong force is based on a mathematical structure called SU3, which is a symmetry group that describes how color charges transform. Without going too deep into the mathematics, the number of gluon types is determined by this symmetry. 3 colors times 3 anticolors gives 9 combinations, but 1 combination is color neutral and does not participate in the strong force, leaving 8 distinct gluon types. Each of these 8 gluons carries a specific combination of color and anticolor charge. For example, one gluon might carry a red anti-blue color charge, another might carry a green anti-red charge, and so on. When a quark emits a gluon, its color charge changes. A red quark might emit a red anti-blue gluon and become a blue quark. The gluon then travels to another quark, say a blue quark, which absorbs the gluon and becomes a red quark. So the colors of the quarks inside the proton are constantly changing. They are not fixed. At one instant, a particular quark might be red. A moment later, it might be blue, then green. The colors shuffle constantly as gluons are exchanged, but the total color of the proton always remains neutral. The 3 quarks always add up to 1 red, 1 green, and 1 blue, even though which quark carries which color is changing all the time. It is like 3 people constantly swapping colored hats. At any given moment, each person has 1 hat, and the 3 hats are always red, green, and blue. But who is wearing which hat keeps changing. This constant exchange, this ceaseless shuffling of color charges through gluon emission and absorption is what defines the interior of the proton. It is not a frozen structure. It is a living, breathing, dynamic system where quarks and gluons are constantly interacting, constantly changing, constantly exchanging color and energy and momentum. The proton is not a thing. It is a process. It is something that is continuously happening, sustained every instant by the exchange of gluons. And if the gluon exchange ever stopped, if somehow the gluons stopped being emitted and absorbed, the proton would immediately cease to exist. The quarks would fly apart. There would be nothing to hold them together. The proton exists only because gluons exist. It persists only because gluons continue to be exchanged. The proton is not an object that happens to contain gluons. The proton is what gluon exchange looks like when it forms a stable pattern. The gluons are not inside the proton. The gluons are the proton, or at least they are the reason the proton exists at all. So when you ask what a gluon actually does inside a proton, the answer is not simple. A gluon does not just sit there. A gluon does not just carry a force passively like a messenger delivering a letter. A gluon is part of the fabric of the proton itself. It carries the strong force between quarks. It changes the colors of quarks as it is exchanged. It carries enormous amounts of energy and momentum. It interacts with other gluons, creating a dense web of strong force interactions. It contributes to the creation of virtual quark-antiquark pairs that pop in and out of existence. And through all of this activity, all of this violent, ceaseless, energetic chaos, it generates almost all of the proton's mass. The proton is a storm, and gluons are the wind, the rain, the lightning, and the thunder. They are everything that makes the storm a storm. Without them, there is no storm. There is nothing. Just three quarks flying away from each other into the void, unable to exist as the proton that makes up the matter you are made of. That quiet, tidy diagram you were shown in school, three little balls sitting in a circle, is as far from the truth as a drawing of a sunny meadow is from the reality of standing inside a Category 5 hurricane. The proton is violent. The proton is dynamic. The proton is mostly energy. And the gluon is the reason for all of it. Everything that makes the proton what it is, everything that gives it its mass, its stability, its identity, all of it traces back to what gluons are doing inside it at every single moment. Now, we touched on something earlier that deserves much more attention. We said that gluons carry color charge, and that this makes them fundamentally different from photons. That might have sounded like a small technical detail. It is not. It is one of the most important facts in all of physics. And understanding why gluons carrying color charge changes everything is the key to understanding why the strong force behaves so differently from any other force you have ever encountered. So let's slow down and really explore this, because once you see what gluon self-interaction means, you will never think about the inside of a proton the same way again. Let's start with something more familiar. Electromagnetism. You know how electromagnetism works, at least in broad terms. You have electrically charged particles like electrons and protons. They interact by exchanging photons. The photon is the force carrier of electromagnetism. When an electron and a proton attract each other, they do so because photons are flying back and forth between them, carrying the electromagnetic force. This is a clean, well-behaved interaction. The electron emits a photon. The proton absorbs it. The force is transmitted. Simple. Now, here is the critical thing about photons. Photons are electrically neutral. They have zero electric charge. This means photons do not feel the electromagnetic force themselves. A photon does not attract or repel other photons electromagnetically. Two photons can pass right through each other without interacting at all. You experience this every day without thinking about it. When you sit in a room with the lights on, light from the ceiling lamp and light from the window are both filling the room simultaneously. Those photons are crossing paths constantly, flying through the same space at the same time, and they do not affect each other at all. They do not collide. They do not deflect each other. They do not slow each other down. They just pass right through as if the other photons were not even there. This is why electromagnetism behaves the way it does. The force carriers do not interact with each other. They just carry the force between charged particles, and that is it. This makes the electromagnetic force relatively simple. It gets weaker as you move charged particles farther apart, following an inverse square law. Double the distance, the force drops to 1/4. Triple the distance, it drops to 1/9. The force fades smoothly and predictably with distance. And the reason it fades is that the photons spreading out between the charged particles are not doing anything to each other. They're just dispersing into space, and as they spread out, the connection between the particles weakens. Now let's look at gluons, and this is where everything changes. Gluons carry color charge. Unlike photons, which are neutral with respect to the force they carry, gluons are charged with respect to the strong force. A gluon is not just a messenger, it is a participant. It feels the strong force, just as quarks do. And because gluons feel the strong force, gluons interact with other gluons. This one fact, gluon self-interaction, is the single most important difference between the strong force and electromagnetism. And it leads to behavior that seems almost impossible when you first encounter it. Imagine for a moment that photons did carry electric charge. Imagine that every time an electron emitted a photon, to interact with a proton, that photon could interact with other photons along the way. It could attract them or repel them. It could emit additional photons of its own. Those additional photons could emit even more photons. The space between the electron and the proton would fill up with a cascading mess of interacting photons, all pulling on each other, all generating new photons, creating a dense web of electromagnetic activity between the two particles. Electromagnetism would behave completely differently if photons had electric charge. It would be vastly more complicated, vastly more powerful, and vastly harder to understand. Well, that is exactly what happens with a strong force. Gluons carry color charge. When a quark emits a gluon, that gluon can emit additional gluons as it travels. Those new gluons can emit even more gluons. And all of these gluons interact with each other through the strong force. The space between quarks inside a proton is not empty. It is filled with a dense, tangled, self-interacting web of gluons, all pulling on each other, all exchanging color charge, all contributing to the force that binds the quarks together. This is not a small correction to the simple picture of quarks exchanging gluons one at a time. It is the dominant feature of the strong force. The self-interaction of gluons is what makes the strong force strong. Let me try to make this more concrete. In electromagnetism, if you have two charged particles and you want to calculate the force between them, you can do it to a very good approximation by just considering the simplest exchange, one photon going from one particle to the other. You can then add small corrections for more complicated processes, like a photon briefly splitting into a particle-antiparticle pair and then recombining. These corrections exist, but they are small. The simple picture of one photon exchange gives you about 99% of the answer. The corrections are tiny. In the strong force, this does not work at all. The simplest exchange, one gluon going from one quark to the other, does not give you a good approximation of anything. The corrections are not small, they are enormous. A gluon emitted by one quark can split into two gluons before it reaches the other quark. Those two gluons can split into four. Gluons can merge back together. They can form loops, interacting with themselves. The number of possible paths and interactions between two quarks is staggering, and all of these paths contribute significantly to the force. You cannot ignore them. You cannot treat them as small corrections. They are the main event. This is why quantum chromodynamics, the theory that describes the strong force, is so incredibly difficult to calculate with. In quantum electrodynamics, the theory of electromagnetism, physicists can calculate answers to extraordinary precision. The magnetic moment of the electron, for example, has been calculated to more than 10 decimal places, and the calculation matches the measurement perfectly. It is one of the most precisely confirmed predictions in all of science. In quantums, chromodynamics, calculations at that level of precision are essentially impossible using the same methods. The self-interaction of gluons makes the mathematics explosively complicated. Physicists have had to develop entirely different mathematical techniques, including numerical methods that require enormous supercomputers, just to make predictions about the strong force. But the self-interaction of gluons does not just make calculations harder. It creates physical behavior that is genuinely bizarre. And the most bizarre behavior of all is something called asymptotic freedom, which is perhaps the most counterintuitive discovery in the history of particle physics. To understand asymptotic freedom, think about what happens with the electromagnetic force. When two charged particles are close together, the force between them is strong. As you pull them apart, the force gets weaker. This makes intuitive sense. Things that are close interact more strongly than things that are far apart. Every force you have ever experienced in your daily life works this way. Magnets are stronger when they're close together. Gravity is stronger when objects are close together. It seems like an obvious, universal rule that forces should get weaker with distance. The strong force breaks this rule. Or rather, it follows a completely different rule. When quarks are very close together, almost on top of each other, the strong force between them is actually weak. The quarks barely interact. They behave almost as if they are free particles, not bound to anything. This is the asymptotic freedom part. At very short distances, quarks are nearly free. But as you try to pull the quarks apart, as the distance between them increases, the strong force gets stronger, not weaker, stronger. The farther apart the quarks get, the harder the force pulls them back together. This is the exact opposite of what happens with electromagnetism and gravity. It is as if you had two magnets that barely attracted each other when they were touching, but pulled on each other harder and harder the farther apart you move them. That sounds physically impossible. And with magnets, it is impossible. But with quarks and gluons, it is exactly what happens. This discovery was made in 1973 by physicists David Gross, Frank Wilczek, and David Politzer. It was so important that all three received the Nobel Prize in Physics in 2004. The discovery of asymptotic freedom was a turning point in our understanding of the strong force. It explained why quarks behave as nearly free particles at very short distances, which is what the deep inelastic scattering experiments had revealed. And it explained why quarks can never be pulled apart and isolated, because the force between them grows without limit as you try to separate them. And the reason asymptotic freedom happens is gluon self-interaction. This is where the whole picture comes together. When quarks are very close together, the gluon field between them is relatively simple. There is not much space for gluons to interact with each other. The gluons travel short distances, interact briefly, and the force is moderate. Actually, it is more than moderate. At those tiny distances, the effective coupling between quarks is reduced because of how the gluon self-interactions affect the field. The mathematical details involve something called the running coupling constant. which describes how the strength of the strong force changes depending on the energy or distance scale you are looking at. At high energies and short distances, the coupling constant is small. The force is weak. Quarks are nearly free. But as the distance between quarks increases, the gluon field between them becomes more complex. More gluons appear. Those gluons interact with each other. They pull on each other. They form a dense web of strong force interactions. And instead of the force spreading out and weakening like it does in electromagnetism, the gluon self-interactions cause the force to concentrate. The lines of force between the quarks do not fan out in all directions. They get squeezed together into a narrow tube, a flux tube, connecting the two quarks. As you pull the quarks apart, this flux tube stretches, but it does not thin out. It maintains roughly the same energy density along its length. And since the tube gets longer as the quarks move apart, the total energy stored in the tube increases. More distance means more energy. More energy means a stronger restoring force pulling the quarks back together. This is sometimes described by saying the strong force is like a rubber band or a spring. When the quarks are close together, there is little tension, but as you stretch the rubber band by pulling the quarks apart, the tension increases. The farther you pull, the harder it pulls back. Except, unlike a real rubber band, this one never breaks. It just keeps getting stronger and stronger. Well, actually, something does eventually happen if you put enough energy into pulling the quarks apart. But what happens is not what you might expect. If you pump enough energy into stretching the gluon flux tube between two quarks, the tube does not snap in a way that releases the quarks. Instead, the energy stored in the tube becomes so great that it creates new particles. The energy converts into mass, following Einstein's equivalence of mass and energy. A new quark and antiquark pair materialize out of the energy of the stretched flux tube. And now, instead of having two separated quarks, you have two new bound systems. The original quark pairs up with the newly created antiquark, and the original antiquark pairs up with the newly created quark. You end up with two bound systems where there was once one. You never get a free quark. No matter how hard you pull, no matter how much energy you invest, you cannot isolate a single quark. This is why quarks are confined inside protons and neutrons. The gluon field, the self-interacting web of gluons between the quarks, will not allow it. It grows stronger with distance. It stores more energy the farther you stretch it. And if you stretch it enough, it creates new quarks rather than letting the existing ones go free. The gluons are not just carrying a force, they are creating a prison. A prison made of energy. A prison that responds to every escape attempt by getting stronger. And this prison, this confinement, is entirely due to the self-interaction of gluons. If gluons did not carry color charge, if they were neutral like photons, the strong force would behave like a stronger version of electromagnetism. It would weaken with distance. Quarks could eventually be pulled apart if you applied enough force. The proton would be a loosely bound system, not the tight, energetic, permanently confined structure it actually is. Everything about the proton, its stability, its permanence, its internal energy, comes from the fact that gluons interact with each other. Now, let's go even deeper into what this self-interaction looks like inside the proton. Remember, the proton is about 1 femtometer across. Inside that tiny space, gluons are not just flying back and forth between quarks in neat straight lines. They are doing something much more complicated. A gluon emitted by a quark can split into two gluons before it reaches another quark. This is called a gluon splitting vertex, and it is a process that has no analogy in electromagnetism. A photon cannot split into two photons, but a gluon can split into two gluons because gluons carry color charge and can interact with the strong force field. These two new gluons can each split again, or they can merge back into one, or they can interact with quarks, briefly creating quark-antiquark pairs that exist for a fleeting instant before annihilating back into gluons. The proton's interior is a roiling quantum mess of creation and destruction, with gluons splitting and merging and quarks and antiquarks popping in and out of existence. This is sometimes described as the gluon sea. Inside the proton, surrounding the three valence quarks, there is a sea of gluons and quark-antiquark pairs. These are not permanent residents of the proton. They are virtual particles, constantly being created and destroyed by the energy of the gluon field. But they are real in every measurable sense. When physicists probe the proton at high energies, they detect these sea gluons and sea quarks. They carry momentum. They carry energy. They affect how the proton responds to being hit by other particles. They are as much a part of the proton structure as the valence quarks, and the gluons in this sea outnumber everything else. If you could take an instantaneous census of everything inside the proton, you would find that gluons are the dominant population. There are more gluons than quarks. There are more gluons than anything else. The proton is primarily a gluon system. The quarks give the proton its identity, its electric charge, its quantum numbers, but the gluons give the proton its mass, its energy, its internal structure. The quarks are like the name on a building. The gluons are the building itself. Let me push this point further because it is so essential. When physicists measure the structure of the proton using particle colliders, they characterize what they find using something called Proton distribution functions. These are mathematical descriptions of how the proton's momentum is shared among its internal constituents. And what the Proton distribution functions show is remarkable. At high energies, the proton is dominated by gluons at low values of something called Bjorken X, which roughly describes what fraction of the proton's total momentum a given internal particle is carrying. At small momentum fractions, the number of gluons inside the proton explodes. There are enormous numbers of low momentum gluons filling the proton's interior. This is sometimes called the gluon-dominated regime, and it is the regime that describes most of what is happening inside the proton at any given moment. The dominance of gluons inside the proton has been confirmed by decades of experiments at facilities like the Stanford Linear Accelerator Center, the Hadron Electron Ring Accelerator in Hamburg, and the Large Hadron Collider at CERN. Every experiment that probes the proton's internal structure tells the same story. The proton is mostly gluons, not mostly quarks, mostly gluons. The three valence quarks are the headline, but the gluons are the substance. This is why the gluon is not just a messenger. In electromagnetism, the photon genuinely is just a messenger. It carries the force between charged particles, but it does not contribute to the structure of the atom in any fundamental way. An atom's identity is determined by its electrons and its nucleus. The photons exchanged between electrons and the nucleus are the mechanism of the force, but they do not define what the atom is. If you could somehow remove the photon exchanges for a moment, and just look at the particles, you would still see the atom structure, the nucleus with electrons around it. You cannot do this with gluons. If you remove the gluons from a proton, you would not see 3 quarks sitting there in a triangle. You would see nothing. The quarks would fly apart instantly. The proton would cease to exist. More than that, you would lose most of the proton's mass because most of the proton's mass is stored in the gluon field energy. The gluons are not carrying a message between quarks that could exist without them. The gluons are creating the conditions that allow quarks to exist as a bound state. The gluons are generating the mass. The gluons are defining the structure. The gluons are doing everything. Think of it this way. In electromagnetism, if you have 2 charged particles, the particles exist independently. They have mass, charge, and identity regardless of whether they are interacting with each other. The photons between them are the communication channel, but the particles exist on their own. In the strong force, it is different. Quarks do not exist independently. They cannot exist in isolation. They can only exist inside bound states like protons and neutrons, held together by gluons. The gluons are not just facilitating a relationship between quarks. They are making the quark's existence as observable particles possible. Without gluons, quarks as we know them cannot exist as part of the physical world we observe. This is what makes a gluon so remarkable. It is not just a force carrier. It is a structural element. It is a source of mass. It is a generator of complexity. It is the reason the proton exists. The reason the proton has the mass it has. And the reason the proton is one of the most stable particles in the known universe. The proton stability is extraordinary, by the way. The proton's lifetime has been measured to be at least 10 to the 34th years. That is a 1 followed by 34 zeros. The universe is only about 13.8 billion years old, which is roughly 10 to the 10th years. The proton has a lifetime at least a trillion times longer than the current age of the universe. No proton that has ever been created in any star, in any galaxy, at any point in cosmic history has ever been observed to decay. The proton is essentially eternal, and this incredible stability comes from the gluon interactions inside it. The gluon field creates a bound state so tightly held, so energetically favorable, that there is essentially no way for it to fall apart through the strong force. This stability has consequences for the entire universe. Because protons are stable, hydrogen atoms are stable. Because hydrogen atoms are stable, stars can form and burn for billions of years. Because stars burn for billions of years, planets can form around them and life can develop on those planets. The stability of every atom in your body, the existence of chemistry, the possibility of biology, all of it traces back to the extraordinary stability of the proton. And the stability of the proton traces back to gluons, to the self-interacting gluon field that creates a bound state so strong that nothing in nature can tear it apart. There is one more aspect of gluon self-interaction that deserves attention, and it has to do with the nature of the vacuum inside the proton. In quantum field theory, the vacuum is not empty. Even in what we think of as empty space, quantum fields are fluctuating. Particles and antiparticles are briefly popping into existence and then annihilating. This is true for all quantum fields, but in the case of the strong force, these vacuum fluctuations are particularly intense. Inside the proton, the gluon field is not in a quiet vacuum state. It is in a highly excited state. Gluons are constantly being created and destroyed. Quark-antiquark pairs are constantly appearing and vanishing. The energy density inside the proton is enormous. Every cubic femtometer of the proton's interior contains an energy density far greater than anything found in ordinary matter, greater than the core of a star, greater than the surface of a neutron star. The energy density inside the proton is on the order of 10 to the 34 joules per cubic meter. It is one of the most extreme energy environments in nature. And all of this energy comes from gluons. From their self-interactions, their creation and destruction, their constant exchange between quarks and between each other. The vacuum inside the proton is not empty. It is a churning sea of gluonic energy, a dense, violent, dynamic medium that gives the proton its mass, its structure, and its identity. This is why physicists sometimes say that the proton is mostly empty space, but also mostly energy. The quarks inside the proton are point-like particles. They take up essentially no volume. The gluons are also point-like. If you added up the physical size of every particle inside the proton, you would get essentially zero. The proton is, in some sense, entirely empty space. But that empty space is filled with an incredibly intense quantum field. It is filled with gluonic energy, and that energy is what gives the proton its properties. The proton is a bubble of intensely energetic gluon field with a few quarks embedded in it. The quarks are almost incidental. The gluon field is the main event. So when we ask why gluons are not just messengers, the answer is clear. Messengers deliver information and then step aside. Gluons do not step aside. They are part of the system. They interact with each other. They generate their own force fields. They create the confining potential that traps quarks. They produce the energy that accounts for almost all of the proton's mass. They outnumber quarks inside the proton. They carry about half of the proton's momentum. They form a dense, self-interacting sea of energy that defines the proton's internal structure. A photon connects two charged particles. A gluon creates the world those particles live in. A photon is a telephone call between two people. A gluon is the entire city they live in, the infrastructure, the roads, the buildings, the gravity that holds them to the ground. It is not carrying a message between quarks, it is building the reality that quarks inhabit. That is the power of self-interaction. That is why the strong force is unlike anything else in physics. That is why gluons are the most important particles you have probably never thought about. And here is one more thing to consider. Every proton in the universe is doing this right now. Every proton in every atom, in every molecule, in every cell in your body. Every proton in every star. Every proton in every planet. Every rock. Every grain of dust in the cosmos. Inside every single one of them, there is a storm of gluons, a raging sea of self-interacting gluon field energy. It is happening at scales too small to see, at speeds too fast to comprehend, with energies too intense to experience directly. But it is happening, right now, inside you, inside everything. The gluon storm never stops. It has been burning inside every proton since the first protons formed in the early universe, less than a millionth of a second after the Big Bang. And it will keep burning for as long as protons exist, which, as far as we know, is forever. The gluon is not a messenger. It is not glue. It is the most active, most energetic, most structurally important particle inside the most common form of stable matter in the universe. And it has been doing its extraordinary work in every proton, in every atom, in every corner of existence for 13.8 billion years without ever stopping, without ever slowing down, without ever resting. It is the engine at the heart of matter itself. Now we arrive at what might be the most stunning implication of everything we have discussed so far. And it has to do with mass. Your mass. The mass of everything around you. The mass of the chair you are sitting in, the ground beneath your feet, the planet you live on, the stars in the sky. Because here is the question that changes everything. Where does mass come from? If someone asked you that question, you might say something about atoms. You might say that things have mass because they are made of atoms, and atoms are made of protons, neutrons, and electrons. And you would be right, as far as it goes. But it does not go far enough. Because if you look inside those protons and neutrons, if you look at the quarks that make them up, you discover something that should stop you in your tracks. The quarks barely contribute any mass at all. Let me give you the numbers. A proton has a mass of about 938.3 mega-electron-volts divided by the speed of light squared. That is the standard way physicists express particle masses, using energy units divided by the speed of light squared, because of the deep connection between mass and energy. For simplicity, physicists often just say the proton has a mass of about 938 mega-electron-volts. Now, a proton contains 2 up quarks and 1 down quark. An up quark has a mass of about 2.2 mega-electron-volts. A down quark has a mass of about 4.7 mega-electron-volts. If you add up the masses of the 3 quarks inside the proton, you get 2 times 2.2 plus 4.7, which equals 9.1 mega-electron-volts. That is the total mass contribution from the quarks themselves. 9.1 mega-electron-volts out of 938.3 mega-electron-volts. That is less than 1%, about 0.97% to be more precise. Let that sink in for a moment. Less than 1% of the proton's mass comes from the mass of the quarks inside it. The quarks, the particles that define what the proton is, the particles that carry its electric charge, the particles that determine its quantum numbers, contribute less than 1% of its mass. Where does the other 99% come from? It comes from energy. Specifically, it comes from the energy of the gluon field and the kinetic energy of quarks and gluons moving inside the proton. The mass of the proton is almost entirely generated by the energy of the strong interaction, the energy of the gluon-driven storm raging inside it. And this is not some vague metaphorical statement. It is a precise, quantitative, experimentally confirmed fact rooted in one of the most famous equations in all of physics. Einstein's equation, E equals mc squared, published as part of his theory of special relativity in 1905. This equation tells us that energy and mass are equivalent. They are 2 forms of the same thing. Mass can be converted into energy, and energy can be converted into mass. The speed of light squared, c squared, is the conversion factor between them. Because the speed of light is an enormous number, about 300,000 kilometers per second, c squared is an even more enormous number. This means a small amount of mass corresponds to an enormous amount of energy, which is why nuclear reactions release so much power. But the equation works in both directions. Just as mass can become energy, energy can become mass. And that is exactly what is happening inside the proton. The energy of the gluon field, the energy of gluons being created, destroyed, splitting, merging, and interacting with each other, plus the kinetic energy of quarks and gluons racing around at nearly the speed of light. All of that energy manifests as mass. The proton's mass is not the mass of its parts. It is the energy of its internal dynamics, expressed as mass through Einstein's equation. This is one of the most profound things in physics, and most people have never heard of it. When you step on a scale and see your weight, you are not measuring the mass of the fundamental particles inside you. You are measuring the energy of the strong interaction inside every proton and neutron in every atom of your body. The quarks in your body contribute less than 1% of your weight. The gluon-driven energy inside your protons and neutrons contributes the vast majority of the rest. You are, in the most literal and scientifically precise sense, made of energy. Let me break this down more carefully, because the energy inside the proton comes from several sources. and understanding each one helps you see how gluons generate mass. The first source is the kinetic energy of the quarks. The 3 valence quarks inside the proton are not sitting still. They are moving at speeds close to the speed of light, confined to a space about 1 femtometer across. Quantum mechanics demands this. There is a principle called the Heisenberg uncertainty principle that says you cannot simultaneously know a particle's position and its momentum with perfect precision. The more precisely you confine a particle to a small region of space, the more uncertain its momentum becomes. And greater uncertainty in momentum means greater average momentum, which means greater kinetic energy. Confining quarks to the tiny space inside a proton forces them to have enormous kinetic energy. They are not gently drifting around. They are screaming back and forth at relativistic speeds, bouncing around inside their femtometer scale prison. This kinetic energy contributes to the proton's mass. The second source is the energy of the gluon field itself. As we discussed, the interior of the proton is filled with a dense, self-interacting web of gluons. These gluons carry energy. They are constantly being created and destroyed. They carry momentum. They interact with each other. The energy stored in this gluon field is enormous relative to the tiny space it occupies. This field energy contributes directly to the proton's mass. In fact, the gluon field energy is the single largest contributor to the proton's mass, larger even than the kinetic energy of the quarks. The third source is the energy associated with the virtual quark-antiquark pairs that constantly pop in and out of existence inside the proton. The gluon field is so energetic that it constantly creates temporary quark-antiquark pairs. These virtual pairs exist for only a fleeting instant before annihilating back into gluons. But while they exist, they carry energy and momentum. Their brief existence contributes to the overall energy budget of the proton, and therefore to its mass. All 3 of these sources, quark kinetic energy, gluon field energy, and the energy of virtual quark-antiquark pairs, are consequences of the strong interaction. They are all driven by gluons. Without gluons, the quarks would not be confined, so they would not have the enormous kinetic energy that comes from confinement. Without gluons, there would be no gluon field energy. Without gluons, there would be no mechanism to create virtual quark-antiquark pairs. Every source of mass inside the proton, other than the tiny contribution from the quark masses themselves, is a consequence of gluon activity. Gluons generate the proton's mass, not directly because gluons themselves are massless, but indirectly through the energy they create, sustain, and concentrate inside the proton. This is an extraordinary thing. Gluons have 0 mass. They are as massless as photons, and yet they are responsible for generating about 99% of the proton's mass through pure energy. Massless particles creating massive structures through the energy of their interactions. It sounds paradoxical, but it is exactly what happens, and it is confirmed by some of the most sophisticated calculations in modern physics. Those calculations come from a framework called lattice quantum chromodynamics, or lattice QCD. Because the strong force is so complicated, with gluons interacting with each other and creating a tangled web of quantum interactions, physicists cannot solve the equations of quantum chromodynamics with pen and paper. The mathematics is simply too complex. Instead, they use supercomputers. In lattice QCD, physicists discretize space-time into a grid, a lattice, and simulate the behavior of quarks and gluons on that grid. They program in the fundamental equations of the strong force and let the computer calculate what happens. The computer simulates the gluon field fluctuating, quarks moving, gluons being exchanged, and self-interacting, everything that happens inside the proton. And then they measure the mass of the proton in the simulation. The results are stunning. When physicists put in only the masses of the quarks and the strength of the strong force, the known value of the strong coupling constant, and let the computer do the rest, The simulation produces a proton mass that matches the experimentally measured value. The calculated mass agrees with the observed mass to within a few percent. This is one of the greatest triumphs of lattice QCD, and one of the strongest confirmations that we understand where the proton's mass comes from. It comes from the energy of the strong interaction. It comes from gluons. In 2008, a collaboration of physicists led by Stefan Durr published a landmark paper in the journal Science reporting a lattice QCD calculation that accurately reproduced the masses of the proton, the neutron, and other hadrons from first principles. The calculation required enormous computational resources. The simulations ran on some of the most powerful supercomputers available at the time. But the results were clear. The proton's mass emerges from the dynamics of quarks and gluons, governed by the strong force. The quark masses contribute only a tiny fraction. The rest is energy. Pure, strong interaction energy, generated by gluons. Now, let me connect this to something you experience every day. Your body contains roughly 7 billion atoms. That is 7 followed by 27 zeros. Most of the mass in each of those atoms comes from the protons and neutrons in their nuclei. And most of the mass in each of those protons and neutrons comes from gluon-driven energy. So when you stand on a scale, when you feel your weight, when you feel the pull of gravity holding you to the earth, what you are really feeling is the energy of the gluon field inside every proton and neutron in your body. Gravity is pulling on that energy because energy has mass, and mass responds to gravity. If you weigh, say, 70 kilograms, then about 69 kilograms of that comes from the energy of the strong interaction inside your protons and neutrons. Only about 700 grams, less than a kilogram, comes from the actual rest mass of the quarks. And even less comes from the mass of the electrons. The Higgs field, which you might have heard of in connection with the Higgs boson, discovered at CERN in 2012, gives quarks and electrons their rest mass. But the Higgs field is responsible for less than 1% of your weight. The other 99% comes from the strong interaction, from gluons. This is worth pausing on. There has been so much public excitement about the Higgs boson, and rightly so. The discovery of the Higgs boson confirmed the existence of the Higgs field, which is the mechanism that gives fundamental particles their mass. Without the Higgs field, electrons and quarks would be massless, and the universe would be a very different place. The Higgs mechanism is genuinely important, but it is important to understand what the Higgs field does and does not do. The Higgs field gives mass to fundamental particles, to quarks and electrons and W and Z bosons. But the mass it gives to quarks is tiny. A few mega-electron volts for up and down quarks, compared to the 938 mega-electron volts of the proton. The Higgs field is responsible for the seed, the small quark masses that anchor the strong interaction. But the vast majority of the mass you experience, the mass of the proton, the mass of you, comes not from the Higgs field, but from the energy of the gluon field. The Higgs mechanism plants the seed. The strong interaction, driven by gluons, grows the tree. If the Higgs field did not exist, if quarks had zero rest mass instead of a few mega-electron volts, the proton would still have most of its mass. The energy of the strong interaction would still be there. The gluon field would still be raging inside the proton. The proton's mass would be somewhat different, because the quark masses do affect the dynamics, but it would not be zero. It would not even be close to zero. Lattice QCD calculations performed in a hypothetical universe where quark masses are set to zero still produce protons with substantial mass. The mass comes from the energy of the gluon field, and that energy exists regardless of whether the quarks have rest mass or not. So when someone says mass comes from the Higgs boson, they are telling part of the story. A small but important part. The full story is that the mass of ordinary matter, the mass of the stuff you and I and the Earth and the stars are made of, comes overwhelmingly from the energy of the strong interaction. From gluons doing their extraordinary work inside every proton and neutron. Let me try to give you a more visceral sense of the energy involved. The energy density inside the proton is almost unimaginably high. The proton has a volume of roughly 4.2 times 10 to the negative 45 cubic meters, and it has a mass energy of about 938 mega electron volts, which corresponds to about 1.5 times 10 to the negative 10 joules. If you divide the energy by the volume, you get an energy density on the order of 10 to the 34 joules per cubic meter. That number probably does not mean much to you on its own, so let me give you some comparisons. The energy density at the center of the Sun is about 10 to the 16 joules per cubic meter. The energy density inside the proton is roughly 10 to the 18 times higher than the core of the Sun. A billion times higher. The center of a neutron star, one of the most extreme environments in the universe, has an energy density of roughly 10 to the 34 joules per cubic meter. That is comparable to the energy density inside the proton. In other words, the energy density inside every proton in your body is roughly equivalent to the energy density at the center of a neutron star. Think about that. A neutron star is the collapsed core of a massive star. It is an object with more mass than the Sun compressed into a sphere about 20 kilometers across. The conditions at its center are among the most extreme anywhere in the universe. And the energy density inside a single proton, a particle 100,000 times smaller than an atom, matches it. Every proton in your body is its own tiny neutron star in terms of energy density. You contain roughly 10 to the 27 protons, each one with neutron star level energy density, and the total mass you feel when you step on a scale is the sum of all that energy across all those protons. This is why the proton is such a remarkable object. It is tiny, it is stable, it seems simple, but inside it contains one of the most extreme energy environments in nature. And that energy is what gives it mass, not quark masses, not the Higgs field, except for the tiny seed, gluon energy, the energy of the storm. There is a beautiful symmetry here that is worth appreciating. Gluons are massless. They have zero rest mass, just like photons. If you could somehow isolate a single gluon, which you cannot because gluons are confined just like quarks, but if you could, you would find it has no mass at all. It is pure energy, pure motion, pure interaction. And yet, when you take a large number of these massless gluons and confine them together with quarks inside a proton, the energy of their interactions generates mass. Massless things creating mass through energy. It is one of the most elegant and counterintuitive results in physics. This result also tells us something deep about the nature of mass itself. In everyday life, mass feels like a fundamental property of stuff. Things are heavy because they are made of heavy material. A rock is heavy because it is dense, solid, substantial. But when you drill down to the fundamental level, mass is not a property of stuff at all. Mass is a property of energy configurations. The proton is massive, not because its parts are massive, but because the energy of its internal dynamics is enormous. Mass is not substance. Mass is energy, organized in particular patterns by the forces of nature. This is a truly revolutionary insight, and it emerged directly from our understanding of gluons and the strong force. Before quantum chromodynamics, before we understood gluons and their self-interactions, we had no explanation for where the proton's mass came from. Physicists knew the proton had a specific mass. They could measure it with extraordinary precision. But they could not explain it from first principles. They could not derive it from deeper physics. It was just a measured value, a number you looked up in a table. Now we can explain it. We can derive the proton's mass from the fundamental equations of quantum chromodynamics. We can show through lattice QCD calculations that the proton's mass emerges naturally from the dynamics of quarks and gluons interacting through the strong force. The proton's mass is not a free parameter. It is a prediction. And the prediction matches reality. This was not always obvious. For decades, The origin of the proton's mass was one of the big unsolved problems in physics. People knew about quarks, they knew about gluons, they knew about the strong force, but proving that the equations of quantum chromodynamics actually produce a proton with the right mass-required computational tools that did not exist until relatively recently. It required lattice QCD methods that had to be developed and refined over many years. It required supercomputers powerful enough to simulate the complex dynamics of quarks and gluons on a discrete space-time lattice. And when those tools finally became available, when the calculations were finally done, the answer came out right. The proton's mass, one of the most fundamental properties of ordinary matter, is explained by gluon dynamics. There is also a connection here to something even bigger. The mass of the proton determines, in large part, the mass of ordinary matter. And the mass of ordinary matter determines, in large part, the structure of the universe. Stars shine because gravity compresses hydrogen gas until the protons at the center are pushed close enough together for nuclear fusion to occur. The mass of the proton determines how much gravitational pressure is needed for fusion. It determines how hot and dense the core of a star must be. It determines how long stars burn, how large they grow, and what elements they produce when they die. If the proton's mass were significantly different, if the energy of the gluon field was slightly stronger or weaker, everything about the universe would change. Stars might burn too quickly or not at all. The periodic table of elements would be different. Chemistry would be different. The conditions necessary for life might not exist. The fact that the strong interaction produces a proton with exactly the mass it has is not just a curiosity of particle physics. It is a condition for the existence of the universe as we know it. And it all comes back to gluons, to massless particles carrying color charge, interacting with each other, generating a dense field of energy inside a space 1 femtometer across, and turning that energy into the mass that holds the universe together. It sounds impossible. It sounds like something out of science fiction, but it is the most carefully verified, experimentally confirmed, computationally validated explanation we have for where the mass of ordinary matter comes from. There is one more piece of this story that deserves attention, and it involves how gluon energy contributes to the mass of the neutron as well. The neutron has a mass of about 939.6 mega-electron-volts. That is slightly heavier than the proton. The difference in mass between the neutron and the proton is about 1.3 mega-electron-volts. This tiny mass difference has enormous consequences. Because the neutron is slightly heavier than the proton, a free neutron is unstable. A neutron sitting alone in space will decay into a proton, an electron, and an antineutrino with a half-life of about 10 minutes and 11 seconds. This process is called beta decay, and it is governed by the weak force, not the strong force. But the reason it happens is that the neutron is slightly heavier than the proton, and nature tends to move toward lower energy states. Where does this mass difference come from? The neutron contains 1 up quark and 2 down quarks, while the proton contains 2 up quarks and 1 down quark. The down quark is slightly heavier than the up quark, by about 2.5 mega-electron-volts, so naively you might expect the neutron to be heavier simply because it has more down quarks, and that is part of the story. But the electromagnetic energy inside the proton and neutron also contributes. The proton has a positive electric charge, so there is electromagnetic energy stored in its electric field. The neutron is electrically neutral, so it has less electromagnetic self-energy. These two effects, the quark mass difference and the electromagnetic energy difference, compete with each other, and the net result is the observed mass difference of about 1.3 mega-electron-volts. But the point is this: the vast majority of both the protons and the neutrons' mass comes from the same source, the energy of the gluon field. Both particles have masses of about 938 to 940 mega-electron-volts, and in both cases, less than 1% of that mass comes from quark rest masses. The gluon field generates the mass of both the proton and the neutron. The tiny difference between them is determined by the small quark mass difference and electromagnetic effects, but the bulk of the mass in both particles is pure gluon-driven energy. This means that when you look at the periodic table of elements, when you look at the mass number of any atom, what you are really looking at is a count of how many gluon storm bubbles are packed into that atom's nucleus. A carbon atom has 12 nucleons, 6 protons, and 6 neutrons, each one containing its own raging gluon field. An iron atom has 56, a gold atom has 197. The mass of each element, the heaviness of each substance, is determined almost entirely by how many gluon-driven energy systems are packed into its atoms. Gold is heavier than iron, not because its quarks are heavier. The quarks are exactly the same. Up quarks and down quarks, the same ones found in every proton and neutron throughout the universe. Gold is heavier because it has more protons and neutrons, which means it has more gluon fields, more strong interaction energy, more of the storm. Mass is not about what kind of stuff you are made of. Mass is about how much gluon energy you contain. You are, right now, being held to the surface of the Earth by gravity, and gravity is pulling on the energy of the gluon fields inside your protons and neutrons. The weight you feel, the force pressing you into your chair, the effort it takes to stand up and walk across a room, all of that comes from gluons, from massless particles generating mass through energy, from the most violent, most dynamic, most energetic process occurring inside the most common building blocks of matter. You are heavy because of gluons. The Earth is heavy because of gluons. The Sun is heavy because of gluons. Everything with mass in the ordinary universe, every atom of every element, owes its mass to the energy of the gluon field. And this is happening everywhere, right now. In every proton in the universe, trillions of trillions of trillions of protons, each one containing its own private storm, each one generating mass from energy, each one held together by massless gluons that interact with each other in ways that create the most stable, most enduring, most energetically dense structures in all of nature. The gluon is massless, and yet it gives mass to almost everything. It has no weight of its own, and yet it is the reason you weigh what you weigh. It cannot be seen, cannot be isolated, cannot be pulled out and examined on its own. But its effects are everywhere. In every atom, in every molecule, in every star, in every grain of dust floating between the galaxies. The gluon is the invisible architect of mass in the ordinary universe. It builds everything out of nothing but energy. And it has been doing so without interruption since the first protons formed in the earliest moments of the cosmos. Now there is something we need to address directly, because it causes enormous confusion, and it has to do with the difference between what happens inside a proton and what happens between protons and neutrons in an atomic nucleus. These are two very different things. They involve different particles doing different jobs at different scales, and mixing them up leads to a completely wrong picture of how the strong force works. So let's separate them clearly. Inside a proton, quarks are held together by gluons. We have spent a great deal of time on this. Gluons carry the strong force between quarks. They are exchanged constantly. They interact with each other. They create the confining gluon field that traps quarks and generates the proton's mass. This is the fundamental strong interaction. It operates at a distance scale of about 1 femtometer, the size of a proton, and it involves quarks and gluons directly. But the proton itself exists inside an atomic nucleus. A hydrogen nucleus is just a single proton, so there is nothing else to hold together. But every other element has a nucleus containing multiple protons and neutrons packed together. A helium nucleus has 2 protons and 2 neutrons. A carbon nucleus has 6 protons and 6 neutrons. A uranium nucleus has 92 protons and 146 neutrons. These protons and neutrons are bound together inside the nucleus by a force, But that force is not the same as the force between quarks inside a proton. It is related to it, but it is fundamentally different in character. The force that holds protons and neutrons together inside a nucleus is called the residual strong force, or sometimes the nuclear force, and the particle most associated with carrying this force is not the gluon, it is the pion. Pions are completely different particles from gluons. A gluon is a fundamental particle, one of the elementary building blocks described by the Standard Model. A pion is a composite particle. It is made of a quark and an antiquark bound together by gluons. So, in a sense, pions are themselves products of the gluon interaction. They exist because gluons bind a quark to an antiquark, but pions play a completely different role in the structure of matter than gluons do. Here is how to think about it. Inside a proton, the strong force is operating at its most fundamental level. Quarks exchange gluons. The gluons carry color charge. The interaction is governed by quantum chromodynamics. This is the primary strong interaction. But when you zoom out to the scale of the nucleus, something changes. Protons and neutrons are color-neutral objects. Remember, the three quarks inside each proton or neutron always combine to produce a colorless state. From the outside, a proton looks color-neutral. A neutron looks color-neutral. So the fundamental strong force, which acts on color charge, should not be able to reach between protons and neutrons. Color-neutral objects should not feel the strong force, just as electrically neutral objects do not feel the electromagnetic force. And yet protons and neutrons do attract each other inside the nucleus. Clearly, some force is holding them together. The force that does this is not the fundamental strong force carried by gluons. It is a residual effect, an echo of the strong force that leaks out from inside the protons and neutrons. And this residual force is mediated primarily by pions. Here is an analogy that might help. Think about atoms and the electromagnetic force. Individual atoms are electrically neutral. The positive charges of the protons in the nucleus are balanced by the negative charges of the electrons orbiting around it. So from the outside, an atom has no net electric charge. You might think that neutral atoms should not attract each other electromagnetically, and in one sense, they do not. There is no long-range electromagnetic force between neutral atoms, but there is a residual electromagnetic interaction between them. It is called the van der Waals force. It arises because even though the atom is neutral overall, the charges inside it are not perfectly distributed at every instant. The electrons are moving around, and at any given moment, one side of the atom might be slightly more negative than the other. This creates a tiny, fluctuating electric dipole, and that dipole can induce a complementary dipole in a neighboring atom, creating a weak, short-range attraction. The van der Waals force is a residual electromagnetic force. It is not the fundamental electromagnetic interaction between charges. It is a leftover, a secondary effect that arises because the internal charge distribution of a neutral atom is not perfectly uniform. The nuclear force between protons and neutrons is analogous. Protons and neutrons are color neutral, but the quarks inside them are not. At any given moment, the color charges inside a proton are distributed in some particular way, and this internal color distribution can create a residual effect that reaches out to neighboring protons and neutrons, attracting them. This residual strong force is what holds the nucleus together. In 1935, the Japanese physicist Hideki Yukawa proposed that this nuclear force is carried by a particle with a mass between that of the electron and the proton. He calculated that the mass of this carrier particle should be about 200 times the mass of the electron, based on the known range of the nuclear force, which is about 1 to 2 femtometers. Yukawa's reasoning was elegant. In quantum field theory, the range of a force is inversely related to the mass of its carrier particle. A massless carrier, like the photon, produces a force with infinite range. That is why electromagnetism reaches across the entire universe. A massive carrier produces a force with a limited range. The heavier the carrier, the shorter the range. The nuclear force has a range of about 1 to 2 femtometers, which corresponds to a carrier particle with a mass of about 140 mega-electron-volts. When the pion was discovered in 1947 by Cecil Powell and his team using photographic emulsions exposed to cosmic rays at high altitude, its mass matched Yukawa's prediction remarkably well. Yukawa received the Nobel Prize in Physics in 1949 for this prediction. It was the first time a Nobel Prize had been awarded to a Japanese physicist. The pion comes in 3 varieties: the positive pion, the negative pion, and the neutral pion. The positive pion consists of an up quark and an anti-down quark. The negative pion consists of a down quark and an anti-up quark. The neutral pion is a quantum superposition of an up quark paired with an anti-up quark and a down quark paired with an anti-down quark. The charged pions have a mass of about 139.6 mega-electron-volts. The neutral pion is slightly lighter at about 135 mega-electron-volts. Now, here is the crucial distinction. The gluon operates inside the proton, binding quarks together through the fundamental strong interaction. The pion operates between protons and neutrons, mediating the residual strong force that holds the nucleus together. These are 2 different scales, 2 different mechanisms, and 2 different particles doing 2 different jobs. The gluon works at the quark level. The pion works at the nucleon level. The gluon is a fundamental particle. The pion is a composite particle made of quarks and gluons. The gluon carries color charge and interacts through quantum chromodynamics. The pion is color neutral and interacts through what can be described as an effective nuclear theory. Think of it in terms of levels of organization. At the deepest level, you have quarks and gluons interacting through the strong force. This is quantum chromodynamics. This is where the gluon lives and works. At the next level up, quarks and gluons form bound states, protons, neutrons, and pions. At this level, the internal details of quarks and gluons are hidden. From the outside, protons and neutrons look like single objects. And the interaction between these objects is described not by gluons, but by the exchange of pions and other mesons. It is a different language for describing physics at a different scale. This is actually a very common pattern in physics. At one scale, you have fundamental interactions between fundamental particles. At a larger scale, those fundamental particles form composite objects, and the interactions between those composite objects look different from the fundamental interactions that created them. Consider chemistry. At the fundamental level, atoms interact through the electromagnetic force between their electrons and nuclei. But when you zoom out and look at molecules, you do not describe molecular interactions in terms of individual electron-proton electromagnetic exchanges. You describe them in terms of chemical bonds, molecular orbitals, and intermolecular forces. These are effective descriptions that capture the behavior at the molecular scale without requiring you to track every single electromagnetic interaction at the atomic scale. The nuclear force mediated by pions is an effective description that captures the behavior of protons and neutrons inside nuclei without requiring you to track every single quark and gluon interaction inside each proton and neutron. But there is a crucial difference in difficulty between these 2 levels. The electromagnetic force between atoms is well understood and relatively easy to calculate because electromagnetism is a well-behaved force. Photons do not interact with each other. The perturbation theory methods that physicists use to make calculations work beautifully for electromagnetism. But the strong force is not well behaved at nuclear scales. Gluon self-interaction makes the fundamental theory, quantum chromodynamics, extremely difficult to calculate with, at the distances relevant to nuclear physics. This is why the pion model was so useful for so long. It gave physicists a way to describe nuclear forces without having to solve the impossibly complex equations of quantum chromodynamics for systems of multiple protons and neutrons. Even today, nuclear physics often uses effective theories based on pion exchange, rather than trying to calculate everything from first principles using quarks and gluons. The fundamental theory is quantum chromodynamics, but applying it to complex nuclei is extraordinarily difficult. Lattice QCD calculations, which we discussed earlier, can handle single protons and neutrons. They are beginning to handle simple nuclei like deuterium, which contains just one proton and one neutron. But calculating the properties of a large nucleus like iron or uranium from first principles using quantum chromodynamics is beyond current computational capabilities. For those systems, effective theories involving pions and nucleons remain essential tools. So the gluon and the pion live in different worlds, even though those worlds are connected. The gluon creates the proton. The pion connects protons and neutrons. The gluon works at the femtometer scale inside individual nucleons. The pion works at the femtometer scale between nucleons. The gluon is responsible for the mass and internal structure of the proton. The pion is responsible for the binding of protons and neutrons into nuclei. Both are essential for the existence of ordinary matter, but they do very different things. Now, let's return to the interior of the proton one final time and look more closely at the dynamic sea that fills it, because this is where everything comes together. We have said that the proton contains 3 valence quarks, 2 up quarks, and 1 down quark. But we have also said that the proton is filled with gluons and virtual quark-antiquark pairs. Let's explore this sea in more detail, because it reveals just how complex and rich the proton's interior truly is. When physicists probe the proton at high energies, using particle accelerators to fire electrons or other particles at protons, and study what comes out, they do not see a simple 3-quark system. They see a complex, layered structure that changes depending on how closely they look. This is one of the most remarkable features of the proton. Its internal structure depends on the resolution at which you observe it. If you probe the proton at low energies, with relatively gentle collisions, you see something that roughly matches the simple picture. 3 quarks bound together. The gluons and C-quarks are there, but they are not obvious at low resolution. It is like looking at a photograph from far away. You see the broad shapes, the main features, but the details are blurred. But as you increase the energy of the probe, as you look more closely with higher resolution, the picture changes dramatically. You start to see the gluons, you start to see the C-quarks, you start to see the full complexity of the proton's interior. At very high energies, the kind of energies reached at the Large Hadron Collider at CERN, the proton looks completely different from the simple 3-quark picture. At these energies, the proton is dominated by gluons and C-quarks. The 3 valence quarks are still there, but they are almost lost in the crowd. They are a small fraction of the total number of particles inside the proton. The gluon sea overwhelms everything else. This is sometimes described using the concept of Proton distribution functions, which we mentioned earlier. These functions describe the probability of finding a particular type of particle inside the proton carrying a particular fraction of the proton's total momentum. At high energies, the gluon distribution function rises steeply at low momentum fractions. There are enormous numbers of gluons carrying small fractions of the proton's momentum. The proton is packed with low momentum gluons. This is sometimes called the small x regime, where x refers to Bjorken x, the fraction of the proton's momentum carried by a given parton. What is happening physically is this. Gluons inside the proton are constantly splitting into pairs of gluons or into quark-antiquark pairs. A single gluon can split into 2 gluons. Each of those can split again. The splitting cascades, producing more and more gluons carrying smaller and smaller fractions of the proton's momentum. At the same time, gluons are merging back together and quark-antiquark pairs are annihilating back into gluons. There is a constant flow of creation and destruction, a quantum equilibrium of splitting and merging that maintains the overall structure of the proton while keeping its interior in a state of perpetual activity. The quark-antiquark pairs that appear in the sea are real in every measurable sense. They carry momentum, they carry energy, they participate in interactions. When a high-energy particle collides with a proton, it can scatter off a C-quark or a C-antiquark just as easily as it can scatter off a valence quark. Physicists have measured the contributions of C-quarks to the proton structure with high precision. They have found that the C contains up and anti-up pairs, down and anti-down pairs, and even strange and anti-strange pairs. Strange quarks are heavier than up and down quarks, so strange quark pairs are less common, but they are there. Even heavier quarks like charm quarks can briefly appear in the C, although they are quite rare because of their higher mass. This means the proton is not just 2 up quarks and 1 down quark. At any given moment, depending on the resolution at which you look, the proton might contain 2 up quarks, 1 down quark, several gluons, a pair of strange quarks that appeared out of the gluon field and will vanish again in an instant, a pair of up quarks that popped into existence from a gluon splitting, and dozens of other gluons at various stages of being emitted, absorbed, split, or merged. The proton is a seething quantum ecosystem, teeming with particles that are constantly being born and dying, all sustained by the energy of the gluon field. And here is something truly striking. All of this activity, all of this creation and destruction of particles, all of this splitting and merging of gluons, all of this appearance and disappearance of quark-antiquark pairs is happening inside a space about 1 femtometer across. A space so small that 100,000 of them side by side would barely span a single atom. And the entire process is governed by one thing: the self-interacting gluon field. The gluons are not just participants in this C. They are the C. They generate it, sustain it, and control it. Without gluons, there would be no C-quarks, because there would be no energy source to create them. Without gluons, there would be no splitting or merging, because those processes require gluon self-interactions. Without gluons, the proton's interior would be empty except for 3 quarks. And those 3 quarks would not stay together because there would be nothing binding them. Let me push the depth of this picture a bit further, because recent physics has revealed something even more interesting about the gluon C. In the early 2000s, physicists at the Relativistic Heavy Ion Collider, or RHIC, at Brookhaven National Laboratory in New York, began colliding gold nuclei at extremely high energies. The goal was to recreate conditions similar to those that existed microseconds after the Big Bang, when the universe was so hot and dense that protons and neutrons could not exist as distinct objects. At those extreme temperatures, quarks and gluons are not confined inside individual protons. They form a new state of matter called the quark-gluon plasma. In a quark-gluon plasma, quarks and gluons roam freely over a region much larger than a single proton. The confining gluon field that normally traps quarks inside protons breaks down at these extreme temperatures, and quarks and gluons spread out into a hot, dense soup. The quark-gluon plasma is thought to have existed in the first few microseconds after the Big Bang, before the universe cooled enough for quarks and gluons to condense into protons and neutrons. What physicists found at RHIC and later at the Large Hadron Collider at CERN surprised everyone. The quark-gluon plasma did not behave like a gas of weakly interacting particles, which is what many theorists had predicted. Instead, it behaved like a nearly perfect liquid. It flowed with almost no viscosity, less viscosity than any other known substance. This strongly coupled quark-gluon plasma, as it became known, showed that even when quarks and gluons are not confined inside protons, their interactions are still enormously strong. The gluon self-interaction does not just create confinement. It creates strong coupling even in the deconfined phase. The gluon field is so powerful that even when it can no longer trap quarks into individual protons, it still binds the quarks and gluons together into a strongly interacting collective state. This discovery gave physicists a new window into the nature of the gluon field and the strong interaction. It showed that the gluon field is not just a mechanism for confinement. It is a medium, a substance, a field that fills space and creates powerful interactions regardless of whether it is confining quarks or not. Inside the proton, the gluon field confines quarks and generates mass. In the quark-gluon plasma, the gluon field creates a liquid of strongly interacting particles. In both cases, the gluon field dominates the physics. It is the main character of the story. These experiments also revealed something important about the early universe. When the universe was a few microseconds old, all of space was filled with quark-gluon plasma. There were no protons, no neutrons, no atoms, no matter as we know it. Just a hot, dense sea of quarks and gluons, interacting through the strong force, flowing as a nearly perfect liquid. As the universe expanded and cooled, this plasma underwent a phase transition. The quarks and gluons condensed into protons and neutrons, like water vapor condensing into liquid water as the temperature drops. This was one of the most important events in the history of the universe. It was the moment when the building blocks of ordinary matter formed, and it was driven entirely by the gluon field. The gluons, through their self-interactions, created the confining potential that trapped quarks into protons and neutrons. The gluon field froze into the configuration we find inside protons today, and that configuration has persisted unchanged for 13.8 billion years. So the gluon storm inside every proton in your body is not just a feature of the proton. It is a relic of the early universe. It is a fossil from the first microseconds of cosmic history, preserved intact inside every atom of ordinary matter since the moment quark-gluon plasma condensed into the first protons and neutrons. The gluon field configuration inside today's protons is essentially the same as it was when the universe was a few microseconds old. It has been running continuously, without interruption, for the entire history of the cosmos. Let me bring everything together now. The proton is not a simple object. It is not three quarks sitting quietly in a ball. It is one of the most dynamic, energetic, complex systems in all of nature. Inside a space 1 femtometer across, a space 100,000 times smaller than an atom, there is a raging storm of quarks and gluons. Gluons are being emitted and absorbed constantly. They are splitting into pairs and merging back together. They are interacting with each other through the strong force, creating a dense, self-referencing web of energy. Quark-antiquark pairs are popping into existence from the energy of the gluon field and vanishing again in an instant. The three valence quarks are racing around at nearly the speed of light, their color charges shuffling with every gluon exchange. And the energy of all this activity, the energy of the gluon field, the kinetic energy of the quarks, the energy of the virtual particles appearing and disappearing, is what generates the proton's mass. 99% of the mass of every atom in the universe comes from this process, from gluons. Massless particles whose interactions create the mass of everything you can see and touch. The gluon binds quarks together inside the proton through the fundamental strong interaction. It carries color charge, it interacts with itself, it creates confinement, the unbreakable prison that keeps quarks from ever being isolated. It generates a field of energy so intense that its energy density rivals the core of a neutron star. And it does all of this silently, invisibly, inside every proton and neutron, in every atom, in every molecule, in every cell, in every star, in every galaxy, across the entire observable universe. The pion, by contrast, works at a different level. It mediates the residual strong force between protons and neutrons, holding atomic nuclei together. Without pions, nuclei heavier than hydrogen could not exist. There would be no helium, no carbon, no oxygen, no iron, no gold, no chemistry, no biology, no life. The pion is essential but it operates at the nuclear scale, between nucleons, not inside them. The gluon builds the protons and neutrons. The pion assembles those protons and neutrons into nuclei. They are partners in the construction of matter, but they work at different scales and through different mechanisms. And all of this, the gluon field, the quark sea, the pion exchange, the nuclear binding, the mass generation, all of it has been happening since the universe was a few microseconds old. Since the quark-gluon plasma cooled and condensed into the first protons. Since the first nuclei formed in the furnace of the Big Bang. Since the first atoms assembled hundreds of thousands of years later. Since the first stars ignited and began fusing hydrogen into heavier elements. Since the first planets formed from the debris of dead stars. Since the first molecules assembled on the surface of one small rocky planet, orbiting an ordinary star in an ordinary galaxy. Since the first living cell emerged from chemistry and began to reproduce. Since the first conscious mind looked up at the sky and wondered what the stars were made of. Every step of that journey, from the Big Bang to you sitting here right now, depended on gluons. Depended on massless particles doing extraordinary things inside protons. Depended on energy becoming mass, on self-interaction creating confinement, on a quantum storm raging inside a space too small to see. You will never see a gluon. No one will. Gluons cannot exist as free particles. They are permanently confined inside protons and other hadrons, trapped by the very force they carry. You cannot pull one out and look at it. You cannot isolate one and study it in a laboratory. They announce their presence only through their effects, through the mass they generate, through the confinement they create, through the scattering patterns they produce when protons are smashed together at enormous energies. Gluons are invisible architects. They build the mass of the universe without ever being seen. They hold matter together without ever being touched. They drive the most energetic process inside the most common particle in existence. And they do it in perfect silence. Hidden inside a space smaller than anything you could ever hope to observe directly. The next time you pick up a rock, or hold a glass of water, or feel the weight of your own body, remember what is happening inside the atoms that make up those objects. Inside every proton and every neutron, there is a storm. A storm driven by gluons. A storm that's been raging since the first microseconds of the universe. A storm that generates the mass you feel in your hand, the weight that holds you to the ground, the substance of everything around you. That storm is the gluon at work. And it is one of the most extraordinary, most powerful, most essential processes happening anywhere in the universe. Not out in the depths of space, not in the cores of distant stars, but right here, right now, inside every atom of everything you have ever known. The gluon does not rest. The gluon does not stop. The gluon does not slow down. It has been doing its work for 13.8 billion years, and it will keep doing it for as long as protons exist, which, as far as we know, is forever.